let's have the first speaker. Yeah, we have the first speaker is Bingzhang Fu. He is a director in Alibaba cloud for this high performance networking. So actually, Bingzhang is a well recognized researcher in this area. I think many of our people know him. And actually, I personally work with him on IDMA for several years in Hong Kong. So yeah, okay, now Mr. Ha.
Thanks, Tom, for the introduction. I'm Bingzhang Fu from Alibaba Cloud. It's a great honor for me to have the opportunity to present our recent work. Today, my topic about the EP load balancing and the EP communication optimization for the inference system of MOE models. Let's begin by looking at the rapid rise of the inference workloads. And absolutely, a large model at the core of its growth. Yeah, I think, as you know, since the emergence of ChatGPT, I think the world entered into what we call the battle of hybrid models. And the construction of the AI infra is faster than ever before. According to the Serial IEA, the global data center power consumption in last year was about 484 TWh, which is nearly doubles the consumption in 2020. And according to the estimation, I think the increase rate will not decrease. And the power consumption will reach to about 950, which double again. What is more important is that almost the increase is driven by the AI applications. If we look closely at the applications, we can find something interesting. I think for the first several years, maybe 3 or 4 years, the industry was mainly focused on the training workloads. But from the start of last year, I think there is a very interesting change had to take place. The change is that the large model can do real job. So consequently, a huge wave of AI agent applications has emerged. According to Serial IDC, there were about 28.5 million agents were deployed last year, and this number is expected to be to reach the 2.2 billion by 2030. So I think this right finger further illustrated this phenomenon. According to the estimation, by 2030, the power consumption of the data center will be consumed. 80% to 99% will be consumed by the inference workload. So that is to say, it is very important to optimize the performance of the inference systems. So when we talk about the optimize the system performance, the first thing we want to figure out is to figure out which part is the most important. Compared to the training workload, I think the business life cycle of the inference workload is a little bit more complex. This figure is a simplified view of the whole business life cycle. For each request from the application, the request will be passed through the scheduler, the net gateway, and the scheduler, and finally reach to the engine. Although this figure is very simplified, but I think that the number listed below can clearly show that the engine, which is the component that actually protects model logics, is at the core of the system. So, in other words, to improve the performance of the inference workload is equals to optimizing the engine performance. So before diving into details, I want to briefly recall what changes in the model architecture recently. I think that maybe you know recently Iago Almeida, a former OpenAI researcher, published a paper titled "Scaling Law." Honestly, he pointed out that there was a big bug in the original scaling law paper. He argued that instead of rapidly increasing the model size, we should scale the model size and training data size proportionally. Actually, I'm not a model expert, but based on what I have observed, I found that the model is not getting smaller. Instead, I found that the data engineers are frantically curating more and more data, and the infra team building more and more systems and provide more compute power. And this together to make the model more capable. So, in my opinion, I believe that the size of the model will continue to increase. So under this assumption, the MOE architecture is which can accommodate a large number of parameters with the same power compute budget is more attractive. Actually, you can see from the table in the beginning months of the 2026 this year, almost all the major open source models adopted the MOE architecture. So today, my talk is entirely focused on the MOE architecture. As we know, the most advantage of MOE architecture is that the FLN layer does not need to activate all the experts for each token. For example, the DeepSeek R1 model has 256 ruling expert and one shared expert. For each token, the FLN layer does not need to activate all the 256 ruling expert. Instead, the gating network will select 8 experts with the highest ruling weights to process this token. This significantly reduces the communications. This good thing. But this inevitably introduces the problem of load imbalance. Let's see the finger example. The x-axis represents the 3 different layers, and the y-axis represents the number of tokens processed by each expert. We can see that the expert with the highest load will process 74 times more than the average. So what problem will be caused by this load imbalance? It is very easy to understand that if you have more tokens to send, to dispatch, to process, you have to count more times. So in this example, the hot CPU will use 155.7 microseconds to dispatch the tokens, and the cold CPU only uses half of the time. This is very easy to understand, right? Because underline that why I say more tokens means more times to dispatch, and also more tokens means you have used more times to do the gene computation. But what is counterintuitive is that you can see that the code GPU spend more time in combination. That's why. Because the expert parallelism inherently introduced the synchronization. After the gene computation, the GPU had to aggregate the results of tokens across the different experts. So the code GPU finished the gene computation faster. So they have to wait for the hot GPU to finish their gene computation. And this will result in a lot of GPU resources are wasted. The second problem, when we have the low load balance, we want to the second thing we want to do is to overlap more communication with the computation. User communication can be totally hidden, so we do not have to worry about the communication efficiency, right? So usually we can use some overlap technology like the two-batch overlap to overlap the computer communication. Basically, the TBO works by splitting one big batch into two smaller ones. And when you do the computation for the first sub batch, you can concurrently load the data for the next sub batch. That sounds good, right? But when we implement it in our application, we found some problems. Finally, we found that the TBO, the analytics performance using the two-batch overlap is worse than the baseline. After investigation, we found that the problem is that when you divide the batch into two small batches, that means you reduce the compute intensity. For example, when the batch size is 128, the attention stage will use 256 microseconds. If the computation scales linearly with the batch size, we expect the attention time should be 128 for the batch size of 264 tokens, but the real result is 190. So that's the reason why the two-batch overlap is not efficient for the scenarios with small batch size. After the overlapping of the computer communication, you may find that there always have some communication technology totally hidden. So therefore, you have to do some deeper optimization for the communication term. So for unlike traditional distributed applications, the AI inference application is diffusion-centric. So in other words, the communication is also diffusion-centric. This figure shows the evolution of diffusion-centric communication over the past decades. We can find that there are lots of changes and improvements. Basically, in short, we can see that the diffusion-centric communication evolved from one single network to parallel scale-out and scale-up network. In the scale-out network domain, the RNA-based technology like secure direct RNA and secure direct async has been developed over the past decades. And the core logic of this evolution is to remove the CPU from the critical communication path. In the scale-up domain, currently taking the NV ecosystem as an example, there are three kinds of mechanisms to move data, including the SMO store, TME, and the code engine. Each of them have different characteristics and is suitable for different scenarios. In short, this is too many. From this figure, you can see that there are too many mechanisms to move data in this AI clusters. So it is very complicated to implement a high efficient communication curve. Even for the natural effort, we often find it is confusing. Today I will talk about mainly for the scale-up network for the two reasons. First, the scale-up network is relatively new, and the second, even the scale-up network used to be constrained within a server. Right now, the supernode or superpod is very popular, and the size of the scale-up network gets bigger and bigger. And a bigger scale-up network poses a lot of challenges on the efficient data communication. Also, taking the NV ecosystem as the example, there are three main mechanism to move data within the scale-up network. The first one we call it the programmed I/O. Programmed I/O is the PIO use the SM load store unit to send and load and store data between the SM register and the remote global memory and the shared memory. Because the PIO use SM to directly control the data movement, so it has the minimal control overhead. So it is very suitable for the transferring of extremely small messages. But the drawback is that because it uses the SM to do the data transfer, so it is very difficult to implement the overlap between computing and communication. The second mechanism is post-driven DNA, also known as copy agent. The copy agent, the benefit is that it does not involve this SM during the data transfer. So it is very suitable for implement the communication overlap. But currently, right now, maybe 2 months later, it will change. Right now, copy agent can only be programmed by the CPU. In other words, it is very highly cost in the control loop. So it is not suitable for transferring small messages. To address this problem from the whole architecture, NVIDIA CPU provides the TMA mechanism. TMA can move data between your local shared memory and remote global memory and shared memory. More importantly, it supports the strategy like TMA, so it is very suitable for transferring tensor data with non-contiguous data placement. In short, we can see that these 3 types of mechanisms each has different distinct advantages and disadvantages. So how to use them together to implement the high performance communication kernel is a very complicated task. So to sum up, to address about 3 technical challenges, we propose a comprehensive solution, and today I will introduce them one by one. First, we have to do the load balancing first. We usually do this by exploiting some EPRD technologies, and we periodically monitor the load on each CPU, and we can periodically redistribute the experts across the system. However, during our deployments with some problems of this solution, first is that migrating expert has a cost, right? If the cost is larger than the benefit, so the migration is counterproductive. Second problem is that even with the load balancing we still can see very severe load imbalance within a single cycle. So we propose following the first step EPRD based on the original one. Compared to the original cost-sharing EPRD, our solution has 3 distinct advantages. The first one is that we only migrate the experts within the high bandwidth scale-up domain to minimize the migration cost. And thanks for the fast development of the scale-up network, the size of the scale-up network becomes very large. So it provides us enough flexibility to do the redistribution. Second, we fuse the load balancing kernel and the dispatch kernel into one kernel. So this can minimize the load balancing overhead. And the third advantage is that we not only consider the compute load, we also consider the communication load. Therefore, we can guarantee that there is no bottleneck along the E2E pipeline. Fabric the load balancing is a good technology, but we found it's not not good enough because we further find another very interesting phenomenon is that for one token, we found that routing ways to specific experts is extremely low. In that case, even drop these tokens does not have any negative impact on the value loss. Based on this observation, we asked each expert to check its workload, whether its load is higher than average. If so, the expert can activate the token drop process. This is an example, as the figure shows. The x-axis represents the different experts, and the light blue bars represent the original number of tokens received by each expert. We can see a severe imbalance, and the dashed line represents the average token received by all the experts. And finally, the dark green bar shows the number of tokens finally dropped without computation. With this active but lossless token drop, we can get 30% improvement of the TPOT. Okay, after doing the load balancing, the next step we want to hide as much as possible communication by the computation. Recall that the TPO two-byte overlap does not fit for the small batch scenarios. It's due to that it has to load all the experts but do very little computation. In other words, very high memory access cost versus very low computation intensity. That makes the two-batch overlap very inefficient for small batch scenarios. To address this problem, we find another very interesting phenomenon. Is that the experts does not depend on each other after the gating logic. So based on this observation, we can load some of the experts and do the computation, and then concurrently we load the other experts. By classifying the experts into subgroups, we can execute the groups in APNet, so the compute and communication can be well overlapped. By doing this per-expert overlapping, we can get at most 70.6% improvement of the TOT and the original TPO. Okay. Finally, I will discuss some about the communication kernel optimization. Actually, there are too many details and a lot of labor work and delivery work, and the optimization solutions are very specific. But I think the underlying principle is very clear. In short, for the small matches and the versus large matches, the optimization solution are totally different. For the small matches, the bottleneck is the control path. So our optimization solution is to avoid all the unnecessary control operations, especially the synchronizations. But for the large matches, the bottleneck is the data path. So our optimization principle is to minimize the volume of data transfer and to improve the communication efficiency. I think I can mention two specific techniques we use. I think it is very interesting. The first one is that from the power architecture, the NVHQ introduced the technology called work specialization. that you can use different words to do different tasks. And SOTA community libraries like PPT also use this technique. But with a large number of runs, because each run will statically occupy the resources, when the number of the runs is large, we can see a lot of register spills. And the register spills will significantly degrade the efficiency of the load store operations. To solve this problem, we carefully fine-tune the resource usage of each work, but we guarantee that there is no register spills in all the cases. Therefore, the performance of the load store instructions can be improved significantly. And the second one is that we support zero copy for all operations and in all scenarios. Therefore, we removed all the redundant data copies between the application bar and the communication bar. So based on the set of these optimizations, we can get consistent performance improvements in all the cases and for different metric size. Okay, to sum up, I think optimizing the inference performance of the large models is a very long journey, and with our initial jobs, in my opinion, I think the low-hanging fruit is gone. But further optimization need to go to deeper. The first direction I think is that the integration of compute and communication to minimize the cost between the kernels. So the second one is that we during the optimizations we face a very challenging of the human resources, because for each case, each scenario, it involves a lot of human efforts to optimize the performance of each kernel. So if there is automated the method to optimize the performance of kernels, I think it will be very high value. And the last one is that I still believe that the communication between the software group and hardware group is not sufficient. And there is a lot of hardware features currently is not fully utilized by the software engineers. So I hope more and more outstanding software engineers can join this exciting task together with us. Okay, thank you very much.
Okay, thank you, Dr. Booth. And questions?
Yes. Thank you. Very nice talk. So basically, your last slide, you have a few takeaways, right? Regarding CCL, you said you should cross the boundary. So regarding this CCL research, in the risk community, tons of work on CCL, right? And can you elaborate a bit more on what's the remaining what's the remaining challenge or opportunity there in CCL still, for example, by this stage from cross the boundary? Can you elaborate a bit more on this? What we can do in the CCL?
Well, when we see the increase of the computer and the communication, that means we can reduce some redundant operations. For example, if you use two separate kernels, the computing kernel will do some computation and then temporarily store the result into the global memory. But the data format may be not actually unique for the next stage. when you can integrate these two kernels, so you can directly convert the data to the format that next stage wants. So there you can save a lot of communication and the memory size cost. And another challenge for the CCR is that right now there is not unified communication library for all the scenarios, especially for the inference workload. You use the classic communication libraries, you use the EP communication library, you use the point-to-point communication library for the PD description and the QK store, right? And these different communication libraries are not so well scheduled, so you can see a lot of traffic collisions on the network. So for do the queues between different kind of traffic is also a very big challenge, but this is not covered in this talk.
Thank you.
Go ahead, and for more questions.
Okay, thank you for the talk. So I'm just wondering, what's the inference performance scheme after the improvement? Because based on our experience in the large scale of the periodic code discrete inference, we don't find the scale network is the bottleneck for the Bingzhang performance. So that's why we must see full scheme.
That's highly depends on the scenarios and the configurations of your application. For the low latency sensitive, for the small batches application, for example, the batch size is 1. So the communication latency will dominate about 40 to 50% of the end-to-end latency. So if you use the CRM network, use the kernel fuse, if you can improve the communication by maybe 20–30%, you can. So it converts to the 10 to 50% to the end-to-end performance. But if you optimize for the high throughput scenarios, then I think it's not too much space to improve.
Is there any published paper or data for this work?
I think the first one is the Silicon Hero this year, but the last one, this very details is job improvement is not published.
Okay, all right, okay.
Did you go ahead?
Hello, thank you. I was wondering how much of this can apply to MOE training as well. Specifically, I know that topic dropping is a common practice, but for example, the load balancing part. Have you tried it? Do you think that applies as well?
Sorry, can you repeat the question?
Yeah. How much of these optimizations could also apply to MOE training, not just?
Okay. I think all the techniques for optimizing the communication can also apply for the training. And token job is only used for the inference applications.
Thank you.
Thank you for the wonderful talk. I have this question about the comment that you made about models getting bigger, right? Continuing to get bigger. As agentic and task-specific, work and workloads increase, do you see the use of more sort of domain-specific models?
So the question is, do we use different kinds of acceleration?
So, I think we can focus on MOE architectures, the latest where many of these models are being built with that architecture. And the model size, and this is just pertaining to the comment you made about the model size continuing to grow, right? And as it continues to grow, it has pressures on the infrastructure in being able to serve. Do you see an alternate sort of environment emerging with agentic tasks, where the models, there'll be many models, but smaller models that you have to serve on the same infrastructure.
Yeah, to be honest, because my work is focused on the public cloud. So our team is responsible for the large models. I'm not familiar with that. Yeah.
Thank you.
Yeah, we still have time for the questions in there. Yes. Okay, maybe I asked one high-level question. You actually said when we do this, we need computing guys and networking guys will get the SDC properly. Do you have any suggestions, particular suggestion as you're running a team or you're actually working with other teams on that? But I see it's rather compact because especially for GPU, you have the computing kernel written by the computation guys and the computing writing the computer kernels, and all these kernels need to fuse behind like running kernel, right? So what's your practice on that? Or suggestions? Maybe suggest a new system hardware, new systems or architecture for the hardware and operations.
Yeah. Okay. I think I can use an example to answer your question. Yeah. The first thing actually we have done is job. We have developed a lot of future kernels. At the beginning, we are very unconfident because we are network guy. We are not confident for do the detailed kernel optimization. But we found that with the help of AI, it is very the final results, the current performance is very good enough because the AI can. Well, I think the AI is something. That's my personal opinion. AI is very helpful for when you are not the expert in this field. But if you are a network field expert, you will see the model is very stupid in network. But you is very smart in the compute. So with the help of AI, you can do this course subject the work. And for a team, I think the people should be one team, not separate the computing network team.
Yeah, right.